In this example of using one-dimensional kinematics, we will look at how the distance required for a car to come to a stop increases with increasing speed. In this situation, we have two cars driving side by side or along a straight line in the same direction. They're not driving side by side. One is driving at a different speed, but at the point where the two cars are side by side, that's when both cars will slam on their brakes. We can assume, or we're told, that both cars have the same braking power, so they both brake at a rate of 4.7 meters per second squared, and both are going to come to a stop. We'd like to know how much farther car B, the one that's going faster, travels before coming to a stop than car A does. We'd also like to be able to figure out what car B's speed is when it passes the same point that car A stops at. At this point, go ahead and pause the video, set up the problem, draw yourself a picture, mark any important motions going on in this problem, any important events, and begin to label the problem so that we have a way of transforming the kinematic equations that were given in our textbook into an equation that applies to this situation. Take a moment, pause the video, do that, then restart the video. So here you can see the way that I've drawn my picture and begun to label it. I gave myself a coordinate axis saying to the right is positive x. I also have labeled my velocities at different points, the 3 different points that are important, where the two cars begin to brake, where car A comes to a stop, and then where car B comes to a stop. I felt that those were the 3 important parts of this problem, and so I drew a picture marking those 3 points. I've also marked that my acceleration, I know these cars are slowing down, so I want my acceleration to be opposite the direction of my velocity for both cars. I noted that both cars are traveling in the same direction, so I've got my velocities marked and they're both pointing in the same direction. And then I began to label things. You'll notice I'm going to solve this algebraically before I plug in my numbers. I know the initial velocity of car A, so this is my VA1. I know the initial velocity or speed of car B. This is my VB1. I also know my acceleration, and I know that it's the same for both cars, so I could write that as acceleration A equals acceleration B equals my acceleration, whatever that turns out to be. And as I think about this, what I'm trying to find out, see, I don't know what this distance, stopping distance for car A is, and I also don't know what the stopping distance for car B is. We might call that delta x13. And I also don't know then what this stopping distance is. This is the one that I'm really after. We could call that delta x23. That tells me how much further car B travels before coming to a stop. Now, as I begin to think about how I'm going to translate the kinematic equations into equations that refer to my problem, I look at this and I see I know an initial velocity and a final velocity for both cars, even though those velocities do not occur at the same point. I know an acceleration for both cars. I don't know the time of any of these events. And one thing to be careful of is these two events where car B reaches distance 2 and where car A reaches distance 2, they don't happen at the same time. So I can't simply find the time it takes for car A to reach distance or position 2 and use that to tell me how when car B reaches position 2 because they don't happen at the same time. At this point, go ahead and pause the video. Look at the 4 kinematic equations. Look at what we know and what we want to know, and see if you can select an equation that will let us solve for something that we'd like to know in one step. Now, this is a problem where to get the actual answer, to get this value that we want to know, we can't do that in one step. But if we could get something else that we might want to know, a distance or a time, in one step, then that's going in the right direction. So go ahead and pause the video, select your equation, see if you can set up an equation for our situation by plugging in the variables that we've selected into the kinematic equations. Once you've done that, go ahead and restart the video. So you can see, of the 4 equations that I had to choose from, I saw that I had initial and final velocities for both cars and an acceleration, and I wanted to know a distance. So this equation using the square of the velocities and the distance and the acceleration was a pretty good bet. But that equation doesn't describe my situation. I want to now insert my variables into this equation. So I come up with an equation that describes the situation I'm trying to answer. You'll notice that I've included a small note to remind me that the acceleration is negative. So when I go to plug in my acceleration, I should include a negative acceleration. So for car A, my final velocity, that's going to be VA2 squared equals VA1 squared minus 2 times my acceleration, which was AA, times delta x12. And there's my equation. Now, it's often useful to plug in your zeros because that'll make that variable drop out of an equation. But otherwise, I'm going to leave this as an algebraic expression so I can get an expression for x12 in terms of my other variables. So I look at this, my final velocity is 0. So that's going to go away. And I'm going to solve this equation now for x12. When I do that, I find that delta x12, so the distance between where the car A starts to brake and where it comes to a full stop, is its initial velocity squared divided by 2 times the magnitude of its acceleration. When I go ahead and plug in my numbers, I'm going to get that that's about 95.7 meters. For car B, I notice that I have the same values. I have an initial value and a final value. And so again, I'm going to use this same equation, plugging in my variables. So I get VB, and in this time, my final velocity is at position 3. And that then is my velocity squared at position 1 plus 2 times my acceleration. So my acceleration is minus the acceleration B. Now delta x 1, 3. You'll notice that the subscripts always have to match. So my final has to match my final, and my initial has to match my initial. Now I could have solved for my velocity at B2 directly. That would have answered the first question. But I'm going to go ahead and answer the second question first, and then we'll come back and answer the first question. Now, at this point, I have an equation that describes the motion of car B using my variables. So I'm going to go ahead and solve that, and I get delta x13 is equal to VB1 squared over 2AB. At least this is what we get when I realize that VB3 is equal to 0. When I plug in my values, I end up with a distance that's 215.4 meters. Now, what I'd really like is I'd like to find out this distance, this delta x23. And so I can do that. There's no special equation. I just recognize that, this distance is the distance B traveled, so delta x13 minus the distance car A traveled, so delta x12. That gives me the distance 23. So algebraically, when I plug in my variables, I get VB1 squared over 2A, where A is again that 4.7 meters per second squared, minus VA1 squared over 2A. Looking at my values, I get 119.7 meters, or about 131 yards, which is more than a football field. So by going 100 miles per hour instead of 70 miles per hour, I end up having more than a football field before I come to a stop. Of course, now we can go back and we can answer the first question, finding out how fast was car B going when it passed the point where car A would end up stopping. I look at this and I realize, now that I've found the distance it took car A to stop, that becomes a known quantity, and now I have an initial velocity, I have a distance, and I, of course, have an acceleration. And so I can still use this same equation. We've used it 3 times now. I can use it to solve for my velocity at B2. Writing it down, I get that VB2 squared equals VB1 squared minus 2 times my acceleration times the distance between point 1 and point 2. At this point, there's nothing to rearrange. This is the value I want to know. I just go ahead and plug in my numbers, and I find that when I solve for VB2, I find out that that is 33.5 meters per second. So it ends up that car B, the faster moving car, by the time it reaches the point where the other car would stop, it's still going faster than the car A was going originally. So you can see maybe why when you're traveling down the highway and you're tired of going 55 and you just would really like to speed, maybe this gives you a clue as to why that's not such a good idea. And especially in adverse conditions, why you should slow down, give yourself a few extra seconds between you and the next car. It could save your life because it's not a matter of reaction time. It's not even a matter of your human ability. It is simply a matter of physics. It takes you further to stop, no matter how good of a driver you are. So take some care while driving, and now you can tell your friends why and answer some questions using physics.